Continuing in Chapter 1, we're moving on to Topic 5, More on Slopes. These are the objectives, fewer than what we've had so far. And again, good notes, good quiz scores. Now, we're looking at slope and parallel lines. Now, what are they talking about here? Well, if we have the slope of one equation, let's say is 5, and the slope of another equation is 5, but the y-intercepts for this one, let's say, is 2, and for this one is 5, where the slopes are the same, the y-intercepts are different, then the lines are going to be parallel lines. Now, this applies to whether they're horizontal, vertical. This one would be positive slope, and something like this would be negative slope. Okay, some background. Now, here they're giving us a specific example, example 1, writing equation of a line parallel to a given line. So usually the way these work, they give us an equation that's in slope-intercept here, 3x plus 1, but they want it to go through a particular point, and they want this line to be parallel to this line. So let's go to the whiteboard to work this out. So what do we need to know to find a parallel line? Well, what's the slope of our original equation? And we see it here. So our slope is going to be 3. Now, the points that we wanted to go through, the new equation, are these. That's an x value, that's a y value. So we could use point slope form, but we can also use slope-intercept form, y equals mx plus b. So what's our y value here? Well, our y value is 5. What's our slope? Well, our slope is 3. What's our x value? A negative 2. Now, what we don't know is what our b value would be. So in a sense, we have to solve for the b. Well, there's no fraction, so we just go 5 equals 3 times negative 2 is negative 6 plus b. Transpose the negative 6 to the other side, becomes a positive 6, so this becomes 11 equals b. So now we rewrite it. Y equals, we know our slope is 3. We need to put the x, and our new value for b is 11. Wow, that's nice. Let's see it in what it looks like here. Now they're putting it in, just substituting into point slope form, which is another way to do that. In fact, let me clear this up so you can see it. Where your y value is 5, it goes into the equation here as a negative 5 because of the negative in the formula. And then your x value is a negative 2, but there's a negative in the formula, so the opposite of a negative 2 makes that a positive 2. Well, let's take a moment to put it in the form slope-intercept, going to our whiteboard. This would be in point slope form. So y minus 5. Now we distribute that and we get 3x plus 6. Transpose our negative 5 to this side. where it becomes a positive 5. So we now have y equals 3x plus 11. So there's the proof, putting it from point-slope form into slope-intercept form. Okay, let's go back to our regular screen and clear this up and go on to our next slide. Now, in this, we need some background information. We want to now find a line that is not parallel, but perpendicular. And the protocol for that, and I'll write it right up here. So if the slope of our first line, let's say, is 4, what would be the slope of a line that is perpendicular to that slope of 4 that would be perpendicular to it? And again, what we're talking about is we have one line and then another line that's going to form a right angle. The symbol for that is an upside down capital T, indicating in a sense a 180 degree, which is a straight line, into two 90s, which are right angles, perpendicular. And the protocol for that would be take the opposite sign of that slope. So this slope is positive. So the new one would have to be negative. And the reciprocal of this. Now, 4 over 1, the reciprocal of that is a negative, opposite sign, 1 over 4. So if we multiply 4 times a negative 1 over 4, the product of multiplying the slopes, if you get a negative 1 as a product, those slopes are perpendicular. Okay. Now, for the horizontal line where it's 0, the line that would be perpendicular to that would be the undefined, the vertical line. That would be perpendicular to the horizontal line. Okay, let's go on. Now let's look at example 2. Write equations of a line perpendicular to a given line. Well, again, the first thing we'd have to do is find out what the slope of this line would be. And we saw that it was, we did it earlier, it's a negative 1/3. So what would be the slope of a line perpendicular to this? Well, it would be its opposite sign, be plus that we don't write, and then the reciprocal of 1/3, which would be 3. So the proof would be 1/3, a negative 1/3, times the reciprocal of that opposite sign, 3 over 1, gives you the product of a negative 1. Now, they're not going to ask us to do an equation like this where we find out what it is. They may ask you in homework, but they're not showing an example, but it's done exactly the same way as we did the earlier one, and we don't want this to be too long. Now, in this slide, we're looking at slope as a rate of change, that if we have an x value that we put into the rule, it gives us our y value. That's that little t-chart that we've been using. So we think of x as the input into the rule. That value of x into the rule gives us an output. Now, since x will determine what y will be, we think of x as the independent variable and y as the dependent variable. And that's what they're talking about here. So a little diagram will suffice. Now let's look at some applications, some word problem as we go on. So for example 3, and we're dealing with slope as a rate of change here. In 1990, 9 million adult men lived alone. In 2008, this many million men lived alone. use this information to find the slope of the linear function representing adult men living alone in the United States. Express the slope correct to 2 decimal places and then describe what it represents. Now again, the slope is going to represent the rate of change. So how do we start this? Well, notice what we have here is 2 sets of ordered pairs. We have the year and 9 million, the new year and 14.7 million. So these are 2 sets of ordered pairs that we can then put into the slope formula. Again, take a moment to write this out. And it's just a matter of copying. I could write it, but it's neatly written here. And we get then this relationship, which is to 2 decimal points, 0.32. So what is this 0.32 in reference to? Well, it's the rate of change. That it's this many million men per year. Okay. Now, moving on, we're going to take a look at average rate of change of a function. Now, in this slide, we're looking at what is called average rate of change. And as we look at it, it has some special symbolism. And if we look at a graph, this blue line may indicate what's going on, but what you've done is you've made this red line, which sort of indicates the average of variation of that blue line. So you pick out a point here, and you pick out a point here on your graph, and you want to find the slope. Now, because it's average, we're going to use this little triangular sign here, which is, the word for it is delta, a Greek symbol. So it's y values, remember, is rise divided by run values. And this is, in a sense, your y over x. And it's delta of y divided by delta of x. Just some fancy terminology here. We're going to do the same thing. We want to figure out what would be the average rate of change. And again, if you're doing this from scratch and you have any kind of data, you can kind of shoot a line. What's the average of that data? Then pick out some points and do this. This will give you the average rate of change. So for example 4 now, find the average rate of change. And here is our function. And they're giving you values. There's x sub 1. There's x sub 2. So we're going to subtract x sub 2, which we're going to cube, from x sub 1, which we're also going to cube. And how many items of data do we have? In a sense, there are 2, or just subtract the x's, I should say, gives you the 2. And you get a rate of change now of 4. Again, what is that? That is the slope. Okay. In example 5 now, we're looking at finding average velocity. But again, we're using slope. And we have a ball that's traveling down some sort of slope. This is our major function. They're asking us from 1 to 2 seconds what is the average velocity? Well, this is our y's here. We're going to go to the delta of s divided by delta of t. Again, it's just y over x in a sense. And here, there probably should be a parenthesis. For some reason, it's not coming out very well. So 4 times our second is 2. 2 to the second power is 4. 4 times 4 is 16. And then 1 squared is 1. 1 times 4 is a negative 4 is negative 4. So this gives us 12 for the top. And then 2 minus 1 for our bottom is 1. So 12 over 1. A ball's average velocity between 1 and 2 seconds is 12 feet per second. Again, pause, take some notes. And for our last example, very similar to the one we've just done, formula is the same, but now it's from 1 second to 1.5 seconds. So again, this one's laid out properly. You're going to square this. This gives you, eventually when you multiply it by 4, 9 feet. This is 4 feet. So this becomes 5 feet. This is going to be 0.5 divided by 0.5. If you put that in your calculator, it comes out 10. And so in 1 to 1.5 seconds, the average is 10 feet per second. Okay, hopefully this is helpful and you have some good notes.